we already acquired the notion of robustly optimal solution, asymptotically optimal, probabilistically complete. And now we will concentrate on optimal sampling-based motion planning methods in the sense of asymptotically optimal and probabilistically complete. So what are the optimal motion planning or sampling-based motion planners? So the PRM and RRT are theoretically probabilistic complete. They provide a feasible solution without quality quality guarantee. But despite of that, they are used successfully in many practical applications. And there was let's say one of the major milestone in 2011. That was the systematic study of asymptotic behavior of randomized sampling-based planners, based actually on the mathematical properties of random geometric graphs, RGG, that has been introduced by Gerbert in 1961 and further studied by Penrose. But in 2011, Karaman and Frazzoli actually considered this and provided it to the robotics community. And what you can see in these animations or these videos is that this is performance of the robot using RRT, and this is RRT star. So this is denser, and this seems to be a robot trying to pick up the cap. And that is the difference. This is not optimal. This seems to be close to the optimal. And based on this study, Karaman and Frazzoli proposed new algorithms that are called RG, rapidly exploring random graphs, or optimal variant of this rapidly exploring random tree, RRT star. So what is the quality of solution for the RRT? We have the algorithm RRT. This is the cost of the best pass, and we are asking what is the cost for some particular iteration. So this is a random variable, and it converts to some value, and we can now ask what is the probability that this value is above the optimal cost. And Karaman and Frazzoli showed that for particular cases, the RRT algorithm with probability 1 never provides optimal solution. So the best pass in RRT converges to a suboptimal solution almost surely. That's the interpretation. So what does it mean? So yeah, in many cases, probably very small problems, this feasible path, not the optimal. So RRT doesn't satisfy a necessary condition for asymptotic optimality. What does it mean? That for some non-zero R, which is below the shortest distance between the goal region and the initial location, the event that this algorithm will provide in an infinite number of samples, the optimal configurations, it occurs only if the kth branch of RT contains vertices outside this bore, centered at Q at the initial configuration for infinitely many k. So it is actually required that the root node will have infinitely many subtrees that extend at least a distance epsilon away from Q init. So this suboptimality is caused by disallowing new better paths to be discovered. Because once we expand, so we are done. So we are not improving the path. So that's one of the main points. And what is studied in rapidly exploring random graph is that we actually need to introduce the notion how to actually improve the path. And it is also related to random geometrical graphs, RGG, sorry. And we need to search for an improving path within some ball radius, and it is captured here. So basically the algorithm is almost like the RRT, except that this is not tree. This is a general graph. We sample, we find the nearest, we steer it, we check it is, we have this Q nearest and Q new, and this is collision free. And now within the region of Q near, which is the graph, which are the nodes in our previous graph, we find the nodes within some radius, and this radius depends on the cardinality and the dimension, and should be properly set up. And then we actually expanded by finding the possible connections between this Q new and Q near, and we are updating it for all of the possible locations. So we are trying to improve the path, not the closest one, but improve within some ball radius. Okay. So how it is working? So at each iteration, the RG tries to connect new samples to all vertices in the R and ball centered at it. So we have this location, and we have some ball, and we check. Can we connect this to the existing nodes, and should this provide a better solution? So we need to reroute the path, the shortest path. So what does it mean? So we have this this gamma. This should be set up like this. There is a Lebesgue measure, dimension of the space, and a volume of the unit ball in d-dimensional Euclidean space. Okay, so and what is quite important is that the rate of decay, the average number of connections attempts, is proportional to the logarithms n. So that's that we are not connecting all the locations, configurations. So what are the RRG properties? It is probabilistic complete, it is asymptotically optimal, its complexity in one step is logarithm, its computational efficiency and optimality, it attempts a connection, it can be bounded by logarithm n nodes at each iteration in average. And we reduce the volume of connection balls as this ratio. Just remember, and we increase the number of connections as log n. But having this, we actually can also improve the existing PRM and RRT towards the asymptotic optimality. So we follow the standard PRM, but again, the connections are attempted between roadmap vertices that are within the connection radius. It's the same. And we also have this in RRT, which is basically a modification without the cycles, because that's tree. The tree roadmap is suitable for non-harmonic dynamics and kinodynamic constraints, because we actually have oriented graph, right? So, and if we have some new connections, we may actually reroute the path. So here are some examples. So this is very, let's say, simple 2D problem, right? But this shows that for RRT, we quickly explore the environment. That's rapidly growing expansion tree. In 10,000 expansions, we have the feasible path, we have quickly feasible path, but it doesn't improve, right? In RRT star, where we actually allowed to reroute and sample more densely, so we will find the optimal solution, most optimal solution in comparison to the RRT. However, question is this the simple case, 2D case? So if you will use without any obstacles, right? So it's not that complicated. But this shows the strength of the RRT star algorithm. We are able to find it. It is probably computation demanding, but we are able to find it. So here is another example in more detail, and you can see the rerouting. And this is the cartoon, and you can see, okay, and now we are improving, but immediately you can ask yourself, okay, that's probably we don't need to sample here. That's the idea how we can improve it. But this is the methodology how to solve almost arbitrary motion planning problem and have the guarantee of asymptotic optimality. But it is computation demanding. So take a look to the sampling-based algorithms regarding the probabilistic completeness. The PRM and SPRM are probabilistic complete. PRM is not asymptotically optimal. SPRM actually is, because I can introduce this this ball. Actually, there is the reconnection. The k-nearest, if you consider the k-nearest implementation of the nearest nodes, it is not complete and asymptotically optimal. RRT is probabilistic complete but not optimal. RRG, PRM star, RRT star are both has both these properties, probabilistic completeness and asymptotic optimality. So the SPRM with the connection radius as a function of, and again this is related to the number of nodes in our covering the free space, and also the dimensionality. So that's not very very fast, right? And that's the reason why informed sampling method has been proposed. And in this example particularly, I would like to show not only the improvements of the sampling-based method, but also the evolution, how it was evolved and what has been introduced as an example that, okay, there is some methodology. It sounds be very powerful, but also computation demanding, and we can work with that. And there are a bunch of modifications, but I would like to highlight the informed RRT star, batch informed trees, and original accelerated bit star or rabbit. And in each part, we actually consider a different part of the sampling-based algorithm to improve the performance. So let's start with the informed RRT. Basically, the modifications are highlighted in red. So it is quite straightforward, right? So, and the idea is that once we have a feasible solution, there was like this solution that we will go. So we don't need to sample. So others. So we can restrict the region where we sample to the area that corresponds to the possible configuration within the distance of the current best solution. So using Euclidean distance for at the beginning or is admissible heuristic. So it's underestimating. So better than that, describing it by words, let's take a look to this demonstration. So this is the path, and now what we can do is that having this distance, we can consider this region, and we can sample locations only inside this region. And because we restrict the area where we sample, we quickly sample locations that contribute to the optimal solution. And that's quite intuitive, and it's significantly improved the real-time performance and doesn't hurt the asymptotical optimality. So basically, we are informed about where we should sample. And these are the demonstrations that shows that now the sampling-based method becomes competitive to shortest path. Even that's still questionable, but you can see the huge difference. So that was one improvement. And the other improvement, which is called batch informed trees, is based on the idea that combining the random geometry graph with a heuristic incremental graph search technique like lifelong planning A star. So random geometry graphs are these theoretical foundations for our rapidly exploring random graph and RRT star. So here we consider that we can sample the locations, so we can create a batch of samples, and we will instantiate this random geometric graph and try to improve the solution. So and we will search the tree using the lifelong planning A star with incremental search to reuse the existing information. So we incrementally add the samples and we consider this in a batch. So it has been proposed in 2015, and again I'll take a look to the animation, and also you can take a look to the YouTube video with some narrative, but I will try to comment it. So we can sample it. We start at the beginning, so we consider the Euclidean distance and sample and enlarge and improve enlarge the number of batches and find a better solution. So it actually improved the performance, even the informed RRT star. This is the bit star. So I will try to start it again. We are not talking about fast marching trees, which is also worth of your interest probably. And you can see that this is not that fast. Okay, take a look to some demonstrations. So, and what is the domain of these algorithms? Also robotic arms, mobile robots as well. But this is high-dimensional configuration space for 1, 2, 3, 4, 5, 6, 2 times. So number of dimensions increase. And another example of showing how we can improve it is using. So first what we did is we inform where to sample. Then we consider that we can do that in a batch, and we can enlarge the search space and improve and add some samples. And in a Rabbit, in regionally accelerated bit star, we consider local motion. So the idea is that if we have such two configurations, and we will use this straight line segment to ask what is the collision free. So we will check, okay, this is collision, this is not suitable expansion. However, if we will use local optimal planner that will consider the shape of the obstacle, we can immediately find such a path around the obstacles, and we can speed up that. So this is the idea, and take a look to some results. Again, it is some cartoon, and this is the evolution of the RRT star inform RRT star batch sampled, and if you remember, we have this notion of homotopy. Yeah, that's what we are looking for. So we are looking to actually find a path and use the local search and find the feasible solution within the same homotopy as the optimal solution. So we optimize the connection and allows, okay, this is in a simple way collision, but we locally optimize the path, the connection between the configurations. We will have a speed up on collision avoiding trajectory within the same homotopy, luckily in the same homotopy class as the optimal solution. So it was a bit improvement. And take a look if there is some, okay, in this case there are planning for aerial vehicle. So, and you see that, okay, this has multiple applications, not only for toy examples, but also for robotic manipulators and some flying drones. And if you are interested in sampling-based methods, I recommend you to take a look to some survey. And this is an example of surveys from 2016. There are a bunch of modifications, okay, that are customized, let's say customized to some kinematic models. They use different metric, different sampling strategy, address the constraints. Most of them are on offline, but also anytime RRT star, it's for online. That's Dubin's car actually, and that's for autonomous cars actually. That can be utilized. So again, for Mitsubishi RRT star. So this is active field. Even though that we have some theory, in 2011 it's actually changed because we have the notion of asymptotic, or we have asymptotically optimal algorithms. We have this strong delta clearance and so on that we utilize to actually characterize the algorithms. And to conclude and have some connection with this D-star light, where we plan something and then we realize, okay, the plan was performed in a map that doesn't correspond to the reality. So this is RRTX, which is in some sense very similar with this D-star that we actually plan, and we execute the plan and realize it's changed. The environment is changed, and we like to reuse the information we have stored in our RRT star. So this is RRTX. That you should be aware, okay, there exist some techniques that can may help solve my problem when I am deploying the robot in an environment which may change before I finish the planning and execute the trajectory.